In Unit 2, we talk about molecular and ionic compounds, their specific structures and their properties, and we also talk about other kinds of bonding like metallic bonding. For this particular section, we're going to focus on ionic and covalent bonding, and we'll touch on metallic bonding, but metallic bonding has its own section that we will talk about in more detail later. So first we're going to talk about what is a bond. And this is a review of general chemistry, but in case you forgot, we have the force that is holding the atoms together. And so we have the different kinds of bonds which will have different kinds of forces depending on what is really holding them together. And so this bond that forms makes a unit of something, whether it's an ionic compound or a covalent molecule. And so in ionic bonds, we have a metal and a nonmetal together, or we have polyatomic ions in the mix, again, depending on their charges based off, being ionic, because ionic is charges. And so cations will lose electrons because when you lose electrons, that means you lose negative charge within an atom or a group of atoms. And so the cation is positive because it has more protons compared to its electrons. Our anions have gained electrons. So regardless of if it's a group or if it is just a nonmetal, the anion is going to gain electrons, and so therefore there are more electrons compared to protons, and so we have a negative charge on that ion. Covalent bonds are nonmetal only, so make sure you know where those are on the periodic table, and the bonds in particular are sharing electrons between the atoms. And so why do compounds form, or why do molecules form? It's because they want to achieve the noble gas electron configuration. So back in section 1.5, we talked about how electron configuration is and the pattern behind it, so make sure that you review that. And so we bond just so we can reach that point. You also may have recalled the octet rule back in Gen Chem, though we don't tend to talk about that as much in AP. All right, ionic bonding. So as a reminder, again, you're either giving and gaining electrons to become ions, then the opposite ions attract. And so these ions are attracted to each other based on the charge of that atom, or rather ion since it's charged, but atom ion, same thing. And so we have our strength of that ionic bond is based off Coulomb's law. So remember to review Coulomb's law from Unit 1. And so you need to be able to use Coulomb's law to describe different things about ionic bonds. In ionic bonds, we tend to focus on the term electrostatic force, which if you see in other resources might be called the electrical force. It also might be called the Coulomb force. So just make sure that you recognize those different vocab terms and that they mean the same thing. And pretty much the term electrostatic force is just the fancy smancy way of saying the attraction of opposite charged ions. And so from Unit 1, you should be able to determine a couple different things. So if you have a higher electrostatic force, then that means you would have a higher melting point or boiling point. If we happen to be talking about those, you should be able to use Coulomb's law to determine this. So that way you can explain it for in, like an MCQ or something like that. You should use electron configuration to know if something is an ion or not. So you should know what an atom is neutrally. And then if you got the E config of it, you can notice if it's ionic or not. So just make sure that you could do that. So again, you should know the baseline of an atom, and then if it's an ion, how that would affect the E config for that. Make sure you know your periodic trends from Unit 1 as well. So we have our ionization energy, or IE. And so IE is just the ability to lose electrons. So for example, metals have a low IE because they can easily lose it. And remember, the trend goes from left to right. It increases, and then from bottom to top it's increasing. So just make sure you remember that. And again, remember why, not just the trend in general. And then we have electron affinity. It has the same trend as ionization energy, except it's about adding electrons, so becoming an anion, essentially. You can see in this picture here where you have an atom of sodium and an atom of chlorine, and then you have a chemical reaction happen, and then you can see when this chemical reaction happens, the valence electron, or the outermost electron on sodium, gets donated to the chlorine, and so now the sodium is a cation with a +1 charge, and this becomes a chloride ion, because remember the anion changes to IDE if it is an element by itself, and then it gained an electron, so it has a -1 charge. In covalent bonds, as a reminder, we have electrons shared between nonmetals to other nonmetals. It could be a group of them, it could just be one atom and another atom of nonmetals, so just remember that. And so in covalent bonds, we have attraction, but we also have repulsion. And so we're going to use the example of the oxygen molecule above in order to talk about the different attractions and repulsions. So first, let's talk about the attractions. So we have the electrons shared between both atoms in the nuclei. So in this example, we have the yellow electrons from the yellow oxygen over here, and then we have the electrons that are all in purple for the purple atom. And so you can see in the middle, we have these electrons here, and they're shared between both atoms. And so these electrons are shared because it fills the octet for the valence electrons here, and it also fulfills the electron configuration if I think about them individually, so it would do that. And so the electrons are shared because of that. And so when I'm talking about the specific attraction here, we have the electrons from one atom is attracted to the nucleus of the other, and vice versa if I talk about each of them separately. So if I talk about the yellow electrons first shared in this covalent bond, so we have the 2 electrons here, notice that they're, in between both atoms, right? Because again, they're in the covalent bond. But because the electrons are negative, and in the nucleus of the purple oxygen, there's protons, which are positive, those are attracted to each other. So again, the yellow electrons are attracted to the protons in the purple. I can also talk about the same with the purple electrons here being attracted to the yellow protons in the middle of oxygen. And so even with these attractions, which is why the bonds form, there's also repulsions happening at the same time. So you want to make sure that you understand that. And so the electrons in the electron cloud in general are repulsed. So electrons near each other technically are both negative, and so they do not attract at all to each other. So these electrons here, for example, if they are near each other, they would rather not be, and so they're repulsed. So remember, electrons are negative. If they're near each other, they're not feeling it. And so the nuclei of both atoms are also repulsive against each other. So the yellow protons that are positive here are repulsed by the protons of the purple oxygen over here. And so you need to remember that there are repulsions too. So why do covalent bonds even happen? We have a balancing act of these attractions versus these repulsions. And so this balancing act will form the lowest bond length possible. So in covalent bonds, we have 2 different types of bonds. We have nonpolar versus polar bonds. And so nonpolar share electrons equally. You'll also see the term nonpolar covalent bonds, which is interchanged with just nonpolar bond. The assumption is it's covalent when we're saying that. And so one example is the oxygen I just talked about. So we have the electrons in the middle here because these are both oxygen. They're going to share those electrons equally. We also have polar bonds. That's when electrons are shared unequally. And we can also say polar covalent bonding too. Again, interchangeably, when we say polar bond, we're assuming covalent. And so you just might see that term also. And so one example of this is water. So here's water drawn in different ways. And so in water, you'll have the different partial charges of water. So you can see here, for example, you'll see the lowercase delta symbol with a positive part, and then you'll see the lowercase delta with the negative part, and that is how we show partial charges for polar bonds, and so we have those here. We also draw dipole arrows. So we draw dipole arrows to show polar bonds. And so the way that a dipole arrow works, I'm going to draw it just on the top before I draw it next to the molecule. So you would draw an arrow, and then on the other side of the arrow, you'll have this plus area. And so when we're showing a polar bond, we can show it by putting the partial positive end here and the partial negative end here. And so partial negative end is again lowercase negative versus lowercase positive. I like to think of the arrow as looking like it has a plus sign at the end and the arrow part pointing at the negative. So when I'm looking at a water molecule here, for example, if I want to look at the bond between this oxygen and the hydrogen over here, I could draw a polar bond for that. And so again, I want to make sure the positive side is at the partial positive and the negative sign is where the arrow is pointing. So that is how I show the polar bond in a molecule. So make sure you know how to show polar bonds in a molecule. We'll be able to figure out what are polar bonds in a moment, but for now, this is what you need to do. You can also show the polar bond of a molecule, or rather if a molecule is polar or not based off having polar bonds, by thinking about it in 3D. And then you'll learn about that with VSEPR. I say VESPR, but VSEPR. And that's an acronym that, again, we'll talk about later if you didn't learn that in Gen Chem. And so you'll use that in order to know if a molecule is polar. And in this case, this molecule is polar. So if I want to show the overall polarity of this molecule, I can also draw a dipole arrow. And so I would draw a dipole. Whoop, 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 and done. And that would be the polarity of the molecule like so. And so when we're drawing this arrow, again, it's called a dipole arrow, we're showing the polarity, again, of the bond or the molecule. You'll also hear the phrase dipole moment. That's just the fancy word for polar. Now, as previously mentioned, we have polar bonds versus a molecule being polar. And so even if a molecule has polar bonds, that does not mean the molecule is polar. We cover this more in section 2.7. I also kind of make a pseudo unit of my own, or a pseudo section rather, is 2.8. So we're going to dive really deep into polar bonds versus polar molecules. Again, you can have polar bonds, but that does not mean the molecule is polar. And we cover this when we talk about the different shapes of molecules and if it's symmetric in 3D. So you do have to think in 3D in order to know whether a molecule is polar. If it doesn't even have any polar bonds, automatically the molecule is going to be nonpolar. But if it has polar bonds, then we have to think in 3D to see if it is going to be a polar molecule or not. So let's recap electronegativity from Unit 1. So let's start with the definition first. So En is an atom's ability to attract electrons to itself. This can reference two different things. We can talk about the electrons within an atom itself and how it attracts from the electrons to the nucleus of an atom. Or we can talk about the electrons in a shared covalent bond in a molecule. So we'll see electrons that are shared, and then if they're shared unequally, we can see how Coulomb's law takes effect on why electrons would be more attracted to one side of a molecule versus another. And so we can talk about the electronic structure of atoms. And so the Bohr models, like you can see here and here, they highlight the distance of valence electrons to the nuclei. So for example, we have lithium. We have the 1s here and then the 2s here. And we can compare that to the hydrogen, which only has a 1s. And so when we think of, for example, Coulomb's law, we can think about how the distance between the nucleus with a proton versus the valence electrons are. So if I'm just looking at valence electrons, hydrogen is very close to 1s. The protons in hydrogen here are very close to this valence electron. Versus in lithium, we have the valence electron here in the 2s versus the protons here. So in hydrogen, it's going to be significantly closer compared to Li. So that's an example from Unit 1. We can talk about C law, Coulomb's law, to talk about radius and charges in a molecule. So for example, we have the HF molecule here. And so we can talk about the shared electrons here in this covalent bond, and we can talk about whether it's polar or not. And we'll talk about more on how to determine polarity in a second. But let me just tell you that from the electronegativity trend, remember that F is the strongest because the trend goes from left to right increasing and from down to up increasing. So fluorine is the highest. We ignore the noble gases because they don't really want to, share their electrons and whatnot. And so we're going to go ahead and focus on fluorine. So fluorine, again, super strong because it is the most electronegative atom in our trend. And so we could talk about how the shared electrons here get shared unequally between the H and the F. And so let's think about Coulomb's law, why, right? So for fluorine has a lot of protons in the middle. It has 9 compared to 1 for hydrogen. And so despite the distance in this 2s orbital, right, and the 1s here, remember that these two electrons are going to be shared between this molecule here. And so the shared electrons are going to be having a stronger pull towards the fluorine because it has significantly more protons. And so because of that, we'll have a partial negative charge on that fluorine versus a partial positive charge here. If I were to draw a dipole arrow, I would make it point towards the fluorine like that, and then have the positive over here. Now we could have the electronegativity table in front of us where it shows the values, and I could do subtraction. If I do subtraction, I could figure out whether something's nonpolar covalent, polar covalent, or ionic. But the ranges of doing those subtractions aren't quite right. It's really a spectrum rather than numbers given on a chart. So you could see here's our EN table chart where they all have values. I could take the difference between them and determine, whether something is nonpolar covalent, polar covalent, or ionic based off these numbers. But the most surefire way of really knowing first if something's ionic versus covalent is what kind of atoms are bonding. Remember, ionic is metal plus non-metal or polyatomic ions versus covalent are nonmetals only. And so we remember our rough trend of the staircase here for the periodic table. These guys are our nonmetals, and then we just include hydrogen because it's one of the weird exceptions, so just remember that. And then anything to the left of the staircase is a metal. So just make sure that you know that. Again, we could take these differences, but it's not exactly the best way of determining bond type. Now, when it comes to knowing whether it's nonpolar or polar, we have a good estimate of that. So I like to call these elements here, and you could see this picture here, as the strong boys. And I'm going to use that in class a lot, that these are the strong boys. These are the strong nonmetals. So you can see here NO, F, and Cl. You could see the values for electronegativity are very high. And so again, I'm going to call these as strong boys. Okay. And then any other nonmetal we're going to consider weak. So if they're not part of this NOFCl group here, we're going to call them the weak nonmetals, okay? So that includes hydrogen and any of these guys here. And so if I have a strong boy nonmetal with a weak boy nonmetal, we're going to have a polar covalent bond. If I have anything with strong or weak, we in general will consider that nonpolar. Is this very scientific? No. But it's very useful for when you're answering a multiple choice thing and you don't have these values in front of you to calculate whether it's going to be polar or nonpolar. So in general, Again, we have the strong boys and we got the weak boys. Know who's bonding together. Know which one's going to make polar versus non-polar covalent bonds. It's honestly unfortunate that you don't get the electronegativity table, but these estimates were good enough. So just remember your strong boys and your weak boys. But yeah, it's easier just to have the values to have a rough estimate of what's polar and non-polar. But again, these are just going to be estimates. And also, this is a spectrum. We can't really for sure say that non-polar is less than 0.4 versus polar being between these numbers. This is just a good rough estimate because, again, everything is a spectrum and we have to see how it interacts and all that stuff. You need to know your general characteristics between ionic versus covalent, but the main part you need to know is why. So some of these we've gone over in Unit 1, some of these we're going to go over in Unit 2 and maybe other units, but the key thing is know why, because a lot of this is very explanation oriented. So let's look at an example here. For example, on ionic and covalent, we're going to look at number 4, about conducting electricity. So in liquids and aqueous solutions, we can have ions freely flowing, because remember liquids in AQ, they're freely flowing, right? And so because they're freely flowing, those electrons can conduct electricity, because literally charged stuff, electricity being charged as well, so that can flow easily. Versus in covalent, we don't have charged ions. So covalents are just sharing electrons and being ever so slightly partially positive or negative, but they're not really supercharged or anything. So that's why they don't conduct electricity even if they were melted or liquid. So again, you need to be able to know why these exist based off what we've learned or are going to learn. Here are some your turn questions that I want you to do yourself before I go over the answers. So try to see if you can explain why the melting point is higher between the two choices, and again, explain why. And then for number 2, use your periodic table to determine whether these bonds are polar or not. And then if they are polar, where would you draw the dipole arrow if this is the bond? So this is the bond here, and if it is polar, is it going this way or is it going that way? So go ahead and try that yourself before I go over the answers. So pause this video and try it. Alrighty, ready? Here we go. We'll talk about the first question. So sodium chloride is going to be the answer, and the explanation is with Coulomb's law. Now, don't write because of Coulomb's law. You actually have to explain it. So I'm going to explain one way of using Coulomb's law to write this answer. So looking at this PT over here, because I'm going to use it as a reference while I talk about my explanation. So sodium has a smaller sized atom compared to potassium. Sodium has 3s, versus potassium has 4s as its energy levels. And so since sodium has a smaller sized atom, its nucleus can attract with a higher electrostatic force between the sodium and chloride ions. Again, potassium has more energy levels at the 4s, so it has a longer distance between the potassium and chloride atoms in the ionic bond. So that's one way of explaining it. You could probably summarize that a little bit more, but that's like my super detailed explanation. And notice in this question, chloride is used for both. That was done very purposefully. It's not a coincidence. A lot of problems will try to do that. If they don't do that, then you have to think a little bit more, but they try to make it simplified when talking about explanations. Now, deciding bonds, if they're polar, nonpolar, or ionic. Again, we think about our strong boys, the N, O, F, and Cl, and then we see who it's bonding to. If there's a dipole arrow, draw it. I didn't show a real dipole arrow because I just typed it and was too lazy to get the dipole arrow. And so here, O is a strong boy, C is not a strong boy, so therefore we're going to have a polar bond. it's going to point towards the strong boy because strong boy strong, right? And then for B, these are both weak nonmetals, and so it's nonpolar. Then this is ionic. We have a metal plus a nonmetal. And then we have a strong fluorine versus a weak hydrogen, so it's polar. It's pointing towards F. This is two strong boys together, so we assume nonpolar. Metallic bonding, we're going to focus in 2.4, but we're going to talk about some general information just to give you a taste of it since this was the intro section. And so metallic bonding is dealing with, as implied, metals. And usually we focus on metal solids. And so we have metal solid here, and you can see they're spaced out in a particular way. And then we have something called delocalized electrons. So you could see in this picture, these electrons and the arrows are showing movement. So that means these electrons can move around freely. They're kind of flowing wherever they feel. And so delocalized is exactly that. The electrons can move around and flow around this metal solid. You can also have different names for these electrons. For example, you might hear sea of electrons or like cloud of electrons. Those are all used interchangeably to mention these delocalized electrons, but this is the fanciest way of saying it. Some examples is literally metals on a periodic table. So literally you can name any of them. So copper by itself or magnesium by itself. We'll again talk more in 2.4 about more details on that, but for now that's what we're going to do. Now, because these electrons can flow, metallic stuff is very good at conducting because, again, if electrons are flowing, well, that means electricity can go. So it's going to be a very, very good conductor. Yeah. In general, this section is pretty easy, right? So, let's just summarize it real quick. We need to know what bonds are, why they form. We have the different types of bonds. We also need to know the different properties of these types of bonds and how they relate and explain those properties. So again, you need to know the properties, but really, 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 you need to be able to explain it because that's the biggest part of the AP test is, yeah, I can know some stuff, but make sure you can actually explain it. All right, that's it for this section. Bye.